So, as we have been saying quite a lot, in order to train our deep learning networks, we will use quite a lot of data. And in this case, we already showed that we are going to use data from this site, Zhao Site 5, where we collected, where we flew our drones to take pictures, and then we broke those pictures down into very nice image patches. And to do that, we use quite a lot of functions. We used functions to read color images or binary masks that the forestry people had prepared for us as annotations. We used the connected components with stats function from OpenCV to transform an image with a series of dots, each of them marking the top of one of our subalpine bushes, into a list of coordinates. And then we used OpenCV's functions with list slicing to create sub-images from our big ortho mosaic, each of them corresponding to one of the subalpine patches. Okay, so when we download the data, you can see it in your own computer if you have downloaded the notebook, but if not, I can show it to you here in the Colab machine. We have start with a mosaic and then the ground truth folder that contains several masks, white and black images, binary images, each of them containing the position of the bushes of one species. And then using all of these functions, we transform all of that into our patches, and we also know what species each patch belongs to. Okay, so this is our data. If that sounded a little bit rushed, then it means that you maybe have not been doing the previous units of the course, because all of this was very detailedly explained in unit 3, connected component for patch extraction. So if you haven't seen that one, go back there and check, and all of these functions here will become much clearer. There is a notebook, there is a video lesson. Here we're going to be using PyTorch, and it's good, especially if you're running this in your own computer, to start with this line. If not, Torch CUDA is available, raise an exception, to make sure that you have installed everything. Also, when we run these notebooks in Colab, it's good to come here and check that we have the correct runtime. So change runtime type, and here we want to make sure that we have a GPU. GPUs in Colab are free as long as you use the GPU and not the TPU, which you need to pay for. Okay, so Google Colab provides us with very convenient, albeit limited, GPU computers. So we are using the free GPU computers in Colab. If you have a GPU in your machine, chances are that it will be faster. So if you do have a GPU board in your computer, I recommend that you download the data and run it there. And if not, you can run it from Google Colab, as I am doing. Okay, so here in the notebook you have quite a lot of discussion on what it means to train a deep learning classifier. But as I already explained quite a lot about that in the description of the previous notebook, I'm not going to stop at it now. I do recommend that you have a read, and that if you have any question, you ask me. The important part is that we are going to be using PyTorch to feed a deep learning model to our data, and because of that we need to prepare our data in a way that PyTorch can process easily and can understand, and that means creating a PyTorch dataset. So we create our class CP dataset that inherits from the PyTorch dataset, and then we need to make a creator method and double underscore init method, a get item, and a len method. And because this will be the method and the class that will move from the images that we saw a bit back, the patches that we saw here, to this dataset class that PyTorch can understand, we need to do this here carefully. I'm not going to stop here because you also have a notebook explaining that in lots of detail in Unit 4, but basically before we had saved all the patches in a folder, each patch with a name that contains the class that the patch belongs to, that the bush that the patch is showing belongs to. And here we read the names of the file, take the class from the name of the file, and then make a list of images and a list of classes that each image in the corresponding position belongs to. Get item, which is a method that PyTorch uses to get the next piece of data, will basically return one of the images in the list along with its label, its class. Okay, so basically get item will always receive an index. We will go to the list of images and retrieve that image, and then also retrieve the corresponding label, the label with the same index. And then there are a couple of technical things that you can read about in the previous notebook. Here we also have a function to break a dataset into training and validation. And I want to stop here for a second to speak about training and validation. We have defined a PyTorch data set, and that can be automatically used to create something called a data loader, which is actually what PyTorch uses, but we don't need to define much in the data loader because the work that we have done for the data set already does that for us. Okay, basically we just create a data loader and pass it the data set that we have defined. But there is an important distinction to be made here between the training dataset and the validation dataset. In the previous notebook, we spoke about how to feed a model that we defined to our data. And basically we were using all the data to find the model that best fit that data. In our work with more complex problems and with deep learning models to solve practical problems, we will consider three different types of data sets. And now we are going to speak in some detail about two of them and just mention briefly the third one. The training dataset will be a part of our data that we will use to fit the model to the data. So just like we did before, and as you will see, it will follow the same structure. So we'll have, when we say that we will have an iterative process, and at each point we will use the model to predict some of the data, we will always be speaking about the training data. So we will divide our data at least in two parts, into training and validation. Training will be used to feed the model to that training data, and we will hope that this training data will be representative of the real problem that we want to solve. Okay? Precisely what representative means in this context is not easy to define, and it's also super important. Basically, The training process that we will be focusing on today and that we already outlined in the previous notebook is an optimization process. We define a criteria, the loss function, and we have some data and some model, and we want to bring the data and the model together. But this is basically a mathematical project. A mathematical problem. We hope that by solving this mathematical problem, we will also be creating a network that can solve a practical problem. In this case, we hope that by taking some of our data, calling it training data, and fitting the ResNet50 model to that data, then when I take some image from some other site in the mountain or from some other mountain, some image from another subalpine bush, and run it through the deep learning model that I have trained, it will classify correctly the species that that bush belongs to. So I'm training with a very specific set of data, but I'm hoping that the resulting deep learning network will be useful to solve the general problem of classifying subalpine bushes into these 6 species. Okay? So I have 2 fundamentally different problems. One is a mathematical optimization problem of my data, the training data that I have on hand, to the by using the deep learning model that I'm using. Okay, so first problem, mathematical problem, optimization to the data and the model, fitting the model to the data as best as I can with that iterative process and in terms of the loss function. That's perfectly defined in mathematical terms, and let's say that's the easy part. However, I don't want to use that. What I want to do, that's not my final goal. My final goal is to solve the real problem, the practical problem of classifying bushes from anywhere, not only in my training data, into the 6 species of subalpine bushes that I'm considering. So I have the optimization problem, the training process, and then the real problem, the one that I want to solve in reality. If the deep learning model that I train using my training data really works to solve the general problem, I will be happy, and I will say that my training network has a strong generalization power. The generalization power is the capacity to solve the problem that I'm attacking with general data and not only with the training data. Okay? Sometimes when I have a lot of data, or as much as I can, I should do this always, I divide my data into training data and testing data. Okay, this is often done by taking just all the data and dividing it randomly. That's not very useful, because if the training data and the testing data have the exact same characteristics in terms of lining, if they include images from the same bushes, for example, I'm sort of cheating. If my training data and the testing data are not the same, but they are very similar because of some artificial thing that I do, then the generalization power is compromised. In general, I want to choose some other set of data that I will usually call the testing data to measure, to give an idea of the generalization power of my network. Not only how good the training process, that's very neatly defined, worked, but whether or not this will translate into something that then I can use in practice. And to measure that, I need to define a second set of data as unrelated as possible to the training data. Hopefully it will be from another site in the same mountain, from a different site in the case of our problem. And then once I have already finished my training process with my training data, and I have fit my model to my training data, I want to try and see how well I do with the testing data, because that has not been part of the optimization process. And if that goes well, if that has a good result, if that predicts the classes correctly, then I will be able to say that probably my deep learning network generalizes. Okay, so I have the training data to fit the model and the testing data to give an indication, an idea of how well things will work in practice when I really want to go to the field and use the deep learning model to solve the actual problem that I want to solve. But here we are not dividing into training and testing, we are dividing into training and validation. What is the validation set? The third and final one. The validation set is a sort of intermediate step between training and testing. The validation step is part of the training process, but is not directly used to feed the data to the model. How do I use it then? I use the training data to change the parameters, as we saw in the other notebook. I'm going to have the predictions of the training data, compute the loss function, and then create the new parameters. This is done only with the training data, okay? But while I'm doing that, I'm computing the loss, how close I am to the training data, how close my model is to the training data at each step, okay? And I am also computing the loss of the validation set. So I have another set of data that's not my training data, that may be similar to it, but that I'm not using to change the parameters of the model, only to see how well I'm doing also in this second set of data. So my optimization process does not see the results, the correct results for the validation set, does not use it to change the parameters of the model, but at the same time that I compute the validation loss, I also compute, at the same time that I compute the training loss, I also compute the validation loss. Why? Well, if at any point my validation loss keeps decreasing and my model gets keeping closer and closer to the validation data, if my model keeps getting closer to my training data, but not to my validation data, so the optimization process goes well, but at some point the validation loss is not progressing in the same way as the training loss, my model keeps getting closer to the training data, but not to the validation data. That's why I have two different models. If that happens, model looks like the training data, but not so much like the validation data, then it means that I'm losing that generalization power, that I'm incurring into an error called overfitting. I'm solving the problem only for my training data. I'm not solving it in general. And that happens because the model is seeing the results that it needs to get for the training set and is only adapting to those. I have the validation set to alert me to this situation. If the training loss keeps getting better but the validation loss doesn't, then I will probably have problems with testing data and so on and so forth. Okay? Validation data is an intermediate step between training data and testing data. Training data only to fit the model to the data, and the model sees at each step the correct answer and adapts itself by seeing that correct answer. The testing data is used when I have finished completely the training model and it gives me an idea of how good I would do in practice, and it should be as different as possible from the training data. And the validation is in between. The validation is part of the training process, but the answers, the correct labels for the validation images are not used directly while training the model. I'm just checking the validation loss and the training loss and seeing if at any point the two begin to separate, then probably I need to stop training because I'm just solving the problem for the training data set. I'm losing generalization power, I'm overfitting.